Valgrind is an open source framework for dynamic binary instrumentation. What's that? It's the process of modifying the instructions of a binary program while it executes. It contains the tools that can automatically find a huge range of memory management and threading bugs, as well as being able to profile programs in detail. There are currently 7 different production-ready tools included in the Valgrind distribution: a branch prediction profiler, 2 heap profilers, 2 thread error detectors, a call graph generating cache profiler, and a memory error detector, memcheck. Let's take a closer look at some of these tools. Memcheck is a memory error detector for C and C++. It finds cases of accessing memory that shouldn't be accessed, for example, overrunning the top of the stack, accessing memory after it has been freed, and overrunning and underrunning heap blocks. It also checks if you're using undefined values, which stems from either values that have not yet been initialized or values that are derived from other undefined values. If you incorrectly deallocate heap memory, memcheck will warn you of mismatched use of malloc or new versus free or delete. Some other things memcheck does is warn you about passing a negative value to the size parameter of a memory allocation function, overlapping source and destination pointers in memcopy, and memory leaks in general. Valgrind simulates the interaction of your program with a CPU cache. It simulates a machine with separate level 1 instruction and data cache and level 2 combined cache, which is actually what most modern chips use. Where there are more than 2 levels of cache, Valgrind will simulate the first and last level cache, since the last level has the most influence on the program execution, since that's the level that communicates directly with main memory, so it's more important. The information actually collected by Valgrind includes instruction and data cache reads and read misses, and data cache writes and write misses. It also counts the conditional and indirect branches executed and mispredicted. Valgrind creates a call graph of functions in a program's execution. The kinds of data it collects includes the number of instructions executed, the relationship to source lines, the relationship between functions, and the number of calls. It can also be configured to run cache simulation and branch prediction, similar to Valgrind, to produce more information about the program. There are then options to present and modify the data collected. Valgrind Annotate is a CLI tool that reads the profiler data and prints a sorted list of functions with optional source code annotations. It can also be visualized by the Valgrind GUI. Valgrind Control is another CLI tool that lets you observe and control the status of a program currently running under Valgrind's control without having to stop the program execution. For example, you can get info about the current stack trace or request counters to be reset or dump profile data to a file. Valgrind is a tool for finding synchronization errors in programs using POSIX pthreads, which is an API containing thread primitives that abstract concepts such as shared address space, thread creation, thread joining, thread exit, mutexes, semaphores, and more. Valgrind detects these 3 types of errors: misuse of POSIX pthreads API, potential deadlocks due to lock ordering problems, and data races, which is accessing memory without correct locking or synchronization. These kinds of problems can result in hard to reproduce timing-dependent crashes, deadlocks, and other issues that are hard to find. Valgrind is designed to work on different CPU architectures and provides abstractions to provide an easy-to-use API for the end user. DHAT, or Dynamic Heap Analysis Tool, examines how programs use heap allocations. It tracks allocated blocks and checks which block every memory access directs to. It shows information about these blocks like size, lifetime, read and write count, and read and write patterns. With this data, it is possible to find allocations with characteristics such as process lifetime leaks, excessive turnover, which is when allocations eat up a lot of heap memory, excessive transience, which is allocations of very short-lived blocks, useless or underused allocations, and blocks with inefficient layout. So how does Valgrind work? The Valgrind framework just-in-time compiles from the binary to a sandbox version of the program. Just-in-time compilation is used to emulate the original binary by compiling fragments of the original binary code just as they are required for execution, hence the name. This allows Valgrind to execute it under a virtual sandbox CPU, where each tool can inject instrumentation during this sandboxing process. For example, memcheck inserts instrumentation to various memory operations and replaces heap implementations from glibc with its own instrumented versions.
Let's take a look at how to use Valgrind to debug a program and what kind of information it gives us. For these demos, we'll be using this demo script we built called demo.sh that builds a given C++ program and then invokes it with Valgrind. These demos will be concerned with memcheck, the default Valgrind tool. The first example is a trivial case of a heap allocation caused by new without a corresponding free, which in our case would be from delete. The first thing that you can see when running it under Valgrind is this heap summary showing us statistics like alloc and free count, in addition to how much was still in use after exit. As you can see, there's 4 bytes in one block still in use by the end of the program, which in our case is due to the leak, but that's not always the case. What's more definite is this following error saying 4 bytes in one block are definitely lost. It tells us that this happened in main, which refers to where the allocation that eventually leaked was made. This is good, but if our function was a lot more complex than the one in this example, that might not be enough to track it down. If we change our demo script to build the program with debug symbols, -G in G++, then we should be able to get much more specific errors. Now we can see that we get the exact file and line number of the offending allocation, which is pretty good. If we now delete that allocation, like so, then we can see that there is no longer any leaks left in the program, which is great. That was a bit of a simple example, so let's look at something slightly more complicated. This example has multiple offending lines of code, one of which happens in a loop, so should occur multiple times. The first error reported by Valgrind is just like before. We have a single block that's definitely lost because we don't have a delete for our new. The second error, however, is for the leak we made in the loop, and it shows that 40 bytes were leaked from 10 blocks from one location. That lines up since this loop ran 10 times, leaking 4 bytes each time, all from the same line of code. Memcheck doesn't just detect memory leaks, but can actually detect a whole host of other memory-related bugs, such as invalid reads and writes. In this demo, we've declared a vector of size 10, and then tried to write to the 11th element. This is undefined behavior because we're overrunning the buffer and writing to memory that we don't own. If we run it under Valgrind, we'll see that all of the heap statistics relating to leaks are okay, but we get this invalid write of size 4 error. What's useful about this error is that it shows us exactly how much we overran the buffer by, 0 bytes in this case. If we change our demo to access v12 and run the demo script again, we can see that it now reports the invalid write as being 8 bytes after the buffer end, which is really useful in tracking down the specific details of errors reported by Valgrind. Valgrind isn't always perfect though. Whilst I previously showed that Valgrind can detect out-of-bound memory accesses, such as in a vector, it isn't always capable of this and can't detect a buffer overrun for a stack or static allocation. This example shows 2 global arrays, v1 and v2, and a memory access on v1 that overflows into the memory belonging to v2. As you can see, Valgrind isn't able to detect this error. Another example of something that Valgrind can't detect is leaks when using custom allocators, and this is because Valgrind's leak analysis tracks the heap itself. In this example, we use mmap, which is a Unix API that allows us to allocate private memory directly from the kernel, which circumvents the heap. For those interested, mmap can be used to allocate executable memory, something you can't do with your typical malloc. As you can see from the output, Valgrind is unable to detect the leaked allocation, and that is because it is not a heap allocation. You might be wondering, why shouldn't you always run programs under Valgrind during development if it can find so many errors for you? One such reason is the performance impact, which is quite high. In this example, we have a simple Fibonacci program which doesn't explicitly have any memory operations, but of course, memory operations are required for the stack. Running without Valgrind only takes 7.4 milliseconds, whilst running under Valgrind takes a whole 212 milliseconds.
To demonstrate the characteristics of Valgrind further, we would like to compare it to a set of tools that you should all be more familiar with: sanitizers. Firstly, as a quick refresh, what are sanitizers? They are compile-time program instrumentation tools that can be baked into C and C++ programs. Functionally, they're similar to some of Valgrind's inbuilt tools. Valgrind's Helgrind is roughly equivalent to Thread Sanitizer, and Valgrind's Memcheck is roughly equivalent to the combination of Address Sanitizer, Leak Sanitizer, and Memory Sanitizer. Except Memcheck is unable to find cases of global or stack out-of-bounds accesses, as mentioned previously, as well as use after return errors, which are when stack variable memory is accessed after its declaring function returns. One large difference between the two toolsets is versatility. As sanitizers instrument at compile time, they require the source code, which then needs to be built using a compatible compiler with the correct flag set. The two main compilers supporting sanitizers are GCC and Clang, meaning that they are also limited to C and C++ programs. Valgrind, on the other hand, is able to analyze programs written in any language, be it ahead of time compiled, JIT compiled, or interpreted. This is because it is able to run on the jitter or interpreter itself while it runs the program. No source code is required, meaning a much wider range of programs can be analysed, as the source code is not always readily available. It also does not require the program to be rebuilt, which, for large programs, is nice to avoid. Another demonstration of versatility is the platforms that both toolsets can run on. Sanitizers are able to run on more operating systems, notably being able to run on Windows, which is a common operating system with a large user base that is not supported by Valgrind. By contrast, Valgrind seems to be more focused on supporting a broad range of instruction architectures, including support for 32-bit and 64-bit variants of x86, ARM, PPC, S390X, and MIPS on Linux, while the sanitizers only support x86 and x86-64. Another large difference between the toolsets is performance. In this case, we will be exploring the execution time overheads that they both create. Address Sanitizer increases execution time by roughly 2 times, Memory Sanitizer by 2 to 3 times, and Thread Sanitizer by 2 to 20 times. It was mentioned previously that performance is where Valgrind suffers, which is clear from the fact that without any instrumentation, Valgrind increases execution time by roughly 4 times. Memcheck, which is the default tool, will increase execution time by 10 to 30 times, Cache Grind by 10 to 100, and Massif by roughly 20. It is also worth noting that while Valgrind is capable of analysing multi-threaded applications, it itself is not multi-threaded and will force the program under test to run on a single core. It's stated on the Valgrind website that for Helgrind, a thread debugger, it is not uncommon to see increases to execution time with a factor of 100. To get a direct comparison between the two toolsets, we can compare the combined slowdown for Address Sanitizer and Memory Sanitizer with Memcheck, as functionally, they're quite similar. The sanitizers increase execution time by a factor of 4 to 6, which is significantly lower than the 10 to 30 seen with Memcheck. Thank you for listening to our presentation, and we're happy to take any questions you might have.